delighted to be here and to be making one of your keynote addresses on the work we do in Oxford. The Oxford team's called Climate Econometrics, and it's been going for longer than this series, which was in a sense named after what we were doing. And the idea is to develop econometric methods that work with climate data. Now, the reason that's interesting is, of course, climate data is made up of two components. There's the natural system that physicists, etc., build into their models. And then there's this slightly awkward thing called human behavior that intervenes and produces the CO2 and the other toxins into the atmosphere that then leads to the problems of climate change. So we need very different methods than the ones that are regularly used in the physical community. They're complementary to conservation of energy-based models, to physical process-based models, but they're very much intended to tackle the fact that the data, the observational records, if you like, are in evolving processes that are subject to abrupt shifts. And we call that wide-sense non-stationarity. And if one doesn't model correctly the non-stationarity that's impinging in the processes, the systems that you'll estimate will not actually work. So we need to have a way of formulating models for all the kinds of wide-sense non-stationarity that comes in. Clearly, stochastic trends are there. There's a lot of stochastic trends that earlier work on climate econometrics has shown that you need co-integration in a number of areas. We've also got quite big outliers. You'll see some enormous outliers in one of the studies I look at. I mean, like 40% of the level of the variable for a period, which is a pretty big outlier. We also have abrupt shifts, that location shifts, so the series goes from one level to another, and it's not picked up by the variables that are observed. We need model selection because we've often got many more candidate variables and observations, and our approach is a variant of machine learning. And then, because there's some very good theory out there in the physical side, we need to retain the theory models unaffected by selections. You've got to divide the process into several bits. In fact, I'll tend to divide it into 3 bits. The theory model, if you like, that's unaffected by selection, so we retain it when selecting other things. The other regular variables, the continuous variables, and then all these indicators that we put in to deal with outliers and location shifts, and we separately deal with those. And then you've got to rigorously evaluate to see if the model is any good. So the applications that we've looked at, and the first 2 are the ones I'll talk about today, the Ice Age glaciation over the last 800,000 years, UK CO2 emissions over the last 160 years, and then we've looked at global CO2 concentrations, we've looked at impacts of volcanic eruptions on temperature reconstructions, we've looked at the costs of misforecasting hurricanes, the damages that will occur to the planet from increased temperatures, from increased CO2 emissions, attitudes and beliefs about climate change. Why is it that people in the central belt of the US deny it's happening? Well, the answer is actually they're cooling. And the Americans call it global warming rather than climate change, which might explain to them why it's actually going on everywhere. And what they're getting is the impact of the changes in the way the climate operates as it warms, and then sea level rise and damage to coastal cities. And the methods are applicable in a wide area. There's cross sections, panels, time series, whatever. And the first 2 that I'll illustrate are obviously just going to be time series. Now, one of the criticisms that we've had about the kind of methods we use is that they're only single equation, but both of the examples here are going to be systems. So let's talk about the 4 basic issues. Model selection for wide-sense non-stationary data, the saturation estimators that we use for picking up outliers and shifts, and that's a major part of the paper. Quite a lot of the saturation estimations published, but the 3 new methods I'll talk about are unpublished. Then modeling UK CO2 emissions and the Ice Age glaciation as examples, and then very brief conclusions. So model selection is ubiquitous, and I find it hard that people will spend ages developing a theory, and it's usually a theory model, which is one of many theory models they've thought about, and that's an issue of selection. They select a particular theory. Now, that's less true in the climate area, where everyone pretty much agrees on what the theory looks like. Then you've got a theory, then there's how you implement it. What functional forms do you use? What parameterization? What's the measure of time? How do you even get the data on it, which is its evidential basis? And then there's empirical specification, which can differ yet again. You think you've got a lovely theory model, you need 1 lag, and then you discover you need 8 lags or something. And then it's evaluation. What methods do you use to evaluate it? What tests do you use? These are all selection issues. And they all matter because the outcome will depend on what decisions you made at every stage. And very often you get no track record in economics of how the theory was formed, how many others were looked at, how it was implemented, why you picked this particular data set and why it's a particular time period, and why you picked the empirical specification you did, and why you evaluated it the way you did. And therefore, you've no idea whether the quality of the model is worth publishing or worth binning, right? And it's a big problem for me with economic empirical analyses. I read them through and I haven't a clue whether they're meaningful or meaningless. And I want to avoid that in the econometric work we do in climate by tracking what we do. So absent omniscience, for empirical modeling, selection's inevitable, it's unavoidable, and it's ubiquitous, and it's often unrecorded. So the issue is not whether to select, but how to select. Because we have to discover what matters. And you'll see that's very important in the 2 examples I'm going to deal with. Because although Ice Age modeling, it's got hundreds of papers out there, I don't think any of them have been approached in quite the right way, as you'll see from my explanation of why I built the model the way I built it. So our software implementation is Autometrics, and Jürgen's here and can answer questions about it. So 5 distinct sub-problems have to be simultaneously resolved. You've got to deal with all of them. The initial formulation, how to ensure all the relevant variables are included. So you need many candidate variables. You often need long lag lengths. You need non-linearities in many situations. Looking back historically to the dozens of empirical models I've analyzed, almost all of them have some form of non-linearity. Okay. So model selection, that makes a big difference. You've got to handle more variables N than observations T in our approach, but it can still deliver quite high success rates in eliminating what's irrelevant or retaining what's relevant. Then the appropriate estimation method depends on the exogeneity and endogeneity status of all the unmodeled variables. Evaluation, you want a well-specified model, and there's a range of tests that have been developed over the decades by econometricians for evaluation. And then there's computation. You've got to handle, in our case, very large numbers of candidate variables, and that requires a fast computational procedure. So we'll tackle these 5 problems by formulation. Autometrics basically automatically creates the lags once you've asked for them. It can create the nonlinear functions and the indicators for the saturation methods. It automatically uses a multi-block tree search algorithm at tight significance levels or retaining the theory-based variables without search. Now, when I explain a lot about the saturation methods, I'm going to use a thing called split half. We look at what happens if you put in half the indicators, select, then drop, and then the other half. But the selection method that's actually used in practice is much more general than that. You've got to automatically assign the status of variables, and once you've got your model, we automatically check that it's well specified, and the multipath block searches, the current version of Autometrics, is extremely fast. So that's how we deal with non-stationary data, handle all these problems practically simultaneously. So we've got 5 saturation estimators, of which several are quite widely used already. Impulse indicators to deal with outliers. You've got an outlier, it's a single thing. It may be a measurement error, it may be a sudden change in the system you're dealing with, and it's relative to the model. The fact that data's got outliers doesn't mean the model will have outliers, and the fact the data doesn't have outliers doesn't mean the models won't have outliers. So it's very much a model-based concept. And very often in the robust statistics literature, you've got to know the model, and then you look for outliers. Well, I think that's a meaningless procedure because you can't know a model. You've got to find the model at the same time as you're finding the outliers that might or might not be associated with that model. And that applies to all of these. And then for location shifts, we've had step indicators for quite a long time. I'll talk a bit about trend breaks and using trend indicators. Nonlinear shifts, like we did with volcanoes, you need to design the indicator to pick up the kind of reaction of the temperature to a large volcanic eruption. And then the most recent one, parameter changes, we've got multiplicative indicator saturation. I'm probably talking to the converted when I go through this small section on impulse indicator saturation and how it's implemented theoretically to understand why you can put in more variables and observations and still get a perfectly sensible answer. So we create an indicator for every observation. It's 1 at that observation and 0 every other one. And we put in half of them, assuming that the number of other variables is smaller than, well, quite a lot smaller than half or a quarter of the sample. And I'm going to discuss it first under the null when there's no outliers and you didn't need to do it. Now, of course, if you didn't need to do it, you hope to find no outliers. But our procedure is based on assuming that you will, in fact, pick up at least one, possibly more, outlier that don't really exist, just because they're large deviations within the distributional assumptions you've made. So we include half the indicators in the intercept and the other variables. We record which indicators are significant. And all that does is it's dumbing out the first half of the observations, and it's estimating things in the second half, which is perfectly respectable. You could have just picked the second half as your data set and not dummied out the first half. But doing that tells you what goes wrong in the first half, conditional on what you observe in the second half. Then you reverse it. You drop the ones in the first half, you put in the second half, and you see what goes wrong in the second half, given what's conditional in the first half. And that's how we explain why you can do this, and it works. The provable properties for impulse indicator saturation come out of a fantastic paper by Søren Johansen and Bent Nielsen, 2009. So for a constant parameter model, yt is beta prime zt plus epsilon. Epsilons, here I've taken independent normal, but they consider a wide range of other distributions, constant mean, constant variance, and the z's are independent of the epsilons, and there's n of them, which is less than t over 2, then under the null of no outliers, the limiting distribution of the estimator you get after doing impulse indicator saturation, which I've denoted beta tilde, it still converges to beta at the usual rate of root t, and that's despite the fact that you've got more variables and observations. So it's a variant of robust estimation, and the limiting distribution of beta tilde is normal in the situation I've done here, but the variance is a bit larger than the conventional variance of sigma squared epsilon capital sigma minus 1, because it's being multiplied by the cost of having done it. But that cost is very small if you choose a small significance level alpha. It's quite close to 1 minus alpha to the minus 1 times a unit matrix. So if we took alpha at 1%, 1 minus alpha to the minus 1 is 1.1%, 1.01%. So you've got a 1% increase in the uncertainty, despite having looked for outliers everywhere in your data set. So it's a small cost to pay for the major gain in finding breaks, outliers, data contamination, etc. And I'll illustrate it today by looking at how we apply it in multiplicative indicator saturation, that should be. Now, many of you have done IIS without knowing it, just as you speak prose without knowing it. So there's recursive estimation as an example, moving windows, holdback, excluding data, chow test. These are all examples of specific implementations of IIS, and they all suffer from two problems. First of all, the rest of the model's got to be known before you can do either. And secondly, they're not using the information that you could have got by looking at what's happening to the indicators over the period outside the one you're using. So if you imagine holdback, you fit it to some period and you leave another period out. Well, if you'd put it out by doing impulse indicator saturation, you could have looked at the values of the indicators and discovered that in fact things are wrong and that the holdback is not just testing the way it's done in some of the literature, trying to control the size of the procedure that they're doing. So step indicator accumulates the impulse indicators and is 1 up to time t and 0 otherwise. Now you can also define steps the other way around. There's 0 up to time t and 1 after that. And it does matter in the theory that follows that we've defined it the way they have, as you'll see when I get to a taxonomy of all the indicator saturation methods that we're working with. Now you can also combine them. Supersaturation was named by Neil Erickson for doing impulse indicator saturation and step indicator saturation. We've puzzled for a long time over the fact that these are perfectly linear. The steps are just accumulations of the indicators. And then the question is, you've now got 2 into t minus 1 indicators because you don't need the first step and you don't need the last because that's the intercept. Do you have to adjust the significance level at which you search for having twice as many, or does the fact that they're perfectly linear mean you don't have to do that? But recent work in his master's thesis at Oxford, Jonas Krull, has shown that you do need to adjust for that. So, for example, if you were to set the significance level at 0.5% and you've 100 observations, then the gauge, which is the proportion of irrelevant indicators retained, was about 1%. So it's actually dealing with 200 observations, if you like, by having put in twice as many indicators, 200 variables. If you don't keep tight significance levels, you can overfit. That can be dealt with, but I see people doing these at rather loose significance levels. So what about trend indicator saturation? Why on earth would you want this? So this is a graph, if you look at the one on the left-hand side, it's UK productivity as output per person per year over the period 1860 to 2016. And you can see it's varied gigantically over time. Is there a point? You can see that the growth rate's quite fast. It slows, it's quite fast, it stabilizes, it's quite fast, and then it dies out completely. Now, if you fit an overall trend line, you get complete nonsense estimates of things that the Bank of England does, for example, of is the economy above or below trend? Well, in the period from 1870 to 1900, you can see the trend line is very flat. And yet, according to this, the economy is well above trend and we've got excess demand. And that's just nonsense. You can't use these things to calculate excess demand. They give very much the wrong result if there are changes in the trend rate. So what trend indicator saturation does is it creates a broken trend for every observation. So the first trend's the first observation, the second trend's the first two, and so on. And then we select across them, and that's the graph on the right-hand side. Now, you might think this is very odd. It took 12 trend lines to describe the whole period. But what's actually happening, if you stop to think about it, say you, go back. That not take me back? Yes, it does. Yeah. Say we had only data here. When you fit trend indicator saturation in a world of broken trends, what it gives you is a trend line you would have got if that had been the whole of your data set. That's the way to think about it. It's not that it's doing something very peculiar. It's just telling you that if you'd had that data, this is a trend. If you'd the next period, that's a trend, and so on. And so it just describes how the trends have evolved over time. And you can see that one of the huge advantages is it says, oops, Britain's in deep trouble. The trend has gone to 0 since 2008, right? It's absolutely flatlined. If you look at the Office of Budget Responsibility forecasts of trends are like this. It says productivity is always going to recover, it's always going to recover, it's always going to recover. They're only now, 11 years on, saying, well, maybe it's not going to recover quite so much, right? And if you don't allow for trend breaks, you get very misleading estimates. So let's talk about multiplicative indicator saturation, because what that's going to do is tell you what the parameter estimate you would have got if you'd used data up to that particular point, and that was the first point at which it changed. But of course, it may have changed at other points, so you have to pick up all these changes to see how the parameter is evolving over time. So you multiply every variable by every step indicator to create a huge number of indicators. And this was first investigated by Oleg Kitov and Morten Tabor in 2015, but they haven't done anything since. I'm afraid I've intervened to try and see what are the properties of it. Will it work when you do it theoretically? And their simulations suggest it works, but we need a bit more than that. Now, if we look back and think about what step indicator is, step indicator is allowing for a shift in the trend. It's multiplying every a shift in the intercept. It's multiplying the intercept by every step and then trying to see if the intercept moves. So that's a location shift. Trend indicator saturation is simply doing the same thing. It's multiplying the trend at every point by the steps. And so multiplicative indicator is just a part of a long sequence in which we take perhaps mean zero stationary variables, which IIS, SIS, and TIS would not detect any change in, because they're all determined by the non-zero effect that those variables have. But even in a world of zero mean changes that Mike Clements and I have shown in a number of papers are very difficult to detect in forecast tests. Indeed, forecast accuracy is often hardly affected at all by the changes in parameters of mean zero stationary variables. But you can pick these up by MIS, as we've shown both theoretically and empirically. Now, how can this work? How can you put in so many things and then find it? And again, just think of the fact that, say you knew where the split was. It happens at time t1. You fit your model up to time t1 and you fit it after time t1. You'd be astonished if you didn't pick up the change in the parameter. And all that MIS is doing is selecting that for you. And if the parameter has shifted at t1, it'll find an indicator close to or at t1, albeit with a bit of added variability. So let's set up a very simple DGP. X is mean 0 and variance 1. That the variance doesn't matter much. Y is 5 plus beta 1 times x. Beta 1 is 10 in a constant world, but at observation 7, it halves. It shifts from 10 to 5. And then we set up our general unrestricted model, which includes x, and then includes all the interactions between the steps and x, which I've called dt, thing here. And we put in, you can actually get off with t minus 3 of them because you don't need one necessarily for the overall level, which is retained throughout, and you may not need one for the intercept period. And then applying autometrics under the null at 1% to this particular example and retaining x, it keeps the variables correctly. When beta 1 shifts to 5 at observation 7, I'll show you in a moment that in fact it looks like it was observation 5, but the program correctly picks up observation 7. So let's move to the graph that might explain this. So this is the non-constant beta, but you've just fitted a constant model. And it doesn't look too bad, but if we put in this split half approach, there's 11 indicators here. So I put in the first 6. It picks up number 5 and says, oh, there's a shift at 5. So we record that, we drop the first 6, we put in the next 5, and now it picks up one at 7 and says, ooh, there's a shift at 7. So now you put them both in and you run the regression of y on the constant x, d5 and d7, and the only one it keeps is d7, because d5 just happens to pick up the fact that later data aren't consistent with the earlier, and that the biggest discrepancy is at observation 5. And so we pick up that there is a shift, and if I graph all of these, so this is the graph you've seen, it's not one you've seen, that's the constant model up here, and that's the residuals unscaled, that's actual deviations. And they're very, very close to the errors that I used to generate the data. This is the one you have seen where there's a shift. And you can see why it gets fooled. At observation 5, you get the biggest residual, even though the break is at 7, right? It's interesting if you fit the constant model, that's where the biggest residual occurs, because the parameter, of course, is neither 10 nor 5. It's something in between, being a weighted average, and that causes the biggest discrepancy at observation 5, and you can see that here. And then this is the set you get after you've done your multiplicative indicator saturation, and you can see these are almost the same as these, except it's picked up observation 7, and there's no shift at observation 7, because although it also picks up the shift, it gets a near perfect fit. Now, with designed indicator saturation, you need to know something about the problem you're studying in order to design them to match the kind of theoretical properties that you will observe. And that here we've done for volcanoes, and they're a kind of shaped like the Greek letter nu, and it's very successful in finding all the volcanoes from 1200 AD to the present, and then you can use that to correct the temperature reconstruction measurements that are produced by dendrochronologists. So let me summarize it. I'll actually jump straight to the summary table. So the methods are down the left-hand side: IIS, SIS, TIS, MIS, and VIS. We had an advisory board meeting yesterday, and I'm slightly hoarse because I talked too much at it. Then, what would you estimate at observation T in the split half method? Well, for IIS, you exactly hit the residual, and it's a perfect fit. With SIS, you're going to get the residual minus the residual 1 period ahead. And it's 1 period ahead because the steps are stopping there at time t. If you did the other ones, you get epsilon t minus 1 minus epsilon t. With TIS, it's the same, but they're divided by t and t plus 1. With MIS, they're divided by the variable and the variable at t plus 1. And for what I've called the volcanic one, it's 1 minus a half, ignoring the little bits that go further. Now, the one in MIS looks very worrying because it's doing this for mean 0. But in fact, the t-test that comes out corrects that. So the t-test for an impulse is inconsistent. It only divides the residual by the standard error of fit. For SIS, it's got that change divided by the standard error and the square root t. For TIS, it's picking up the residuals multiplied by the trend. Remember, these are under the null in the first 2 columns. So this is what you're going to pick up when you do the procedure, when you don't need to do the procedure. And with MIS, you get rid of these problematic division by 0, and they're now multiplied up here, and this can't be 0. So the t-test that you're going to use to make the decision, should you allow for a shift or not, works very well. And with the volcanic one, it's the same. And that then leads to these non-centralities if, in fact, there is a shift of size lambda, which in the first line is just an impulse. In the second, it's a step shift from observation T1. In the third, it's a break in the trend from T1. In the fourth, the parameter of the zero mean variable shifts at T1. And the fifth, the volcano explodes at T1. Now, these are if you do split half. And the reason you don't want to do split half is these are not very good. And when you do split half, you eliminate all the irrelevant indicators, particularly when you do it at a very tight significance. And then you end up, if you hit the right split, which is T1, obviously it has no effect on impulse indicator saturation. It gives you a huge increase in power, root T1 divided by root T2 times root T2 for cis. So it's very good at picking up step shifts. It's hugely good at picking up trend shifts. It's t to the 3 upon 2, so it's got enormous power. For MIS, it's not fantastic. It's multiplied by where it occurs. R1 is T1 over T, so it's how far through the sample it occurs, and it's symmetric. It's R1 times 1 minus R1, and it's multiplied by the variability of the Z. So it actually does matter that your Z's have got lots of variability, and you should think of lambda times sigma Z as really being what the shift is in the parameter in that setting. And then for the volcano ones, we've shown it's very good at picking that up. It's quite a complicated calculation for root TD. So now we'll start applying these. And I want to begin with the ice ages. And it's quite clear that up until about 1840, nobody knew about ice ages. Louise Agassiz noticed that glaciers in Switzerland ground up the land underneath them as they were moving. And he measured how fast they moved. And then he came to Scotland and toured Scotland, looking at the landscape to see if the Scottish landscape reflected glaciers, and discovered on an enormous scale, which he called a great ice age, must have hit Scotland at some point. Then Archibald Geikie, in 23 years later, well, he did it much earlier, but published, found plant fragments between the layers of glacial deposits. People knew there were glacial deposits in layers, but they didn't know that there actually must have been warm periods between them, which is why there are ice ages. There's ice age and then a warm interglacial stadia, a warm age, and so on. And then James Kroll, and for those of you who are coming into this discipline from other ones, he was a janitor in a school. He cleaned the blackboards in the school, but he read the blackboards and he taught himself the mathematics and the astronomy, and he worked out theoretically how the Earth's orbit variations could cause ice ages. And he publishes a graph in 1875 that you can still see in the Royal Society of Edinburgh's library, showing when they would all occur. Well, he's the one who does them backwards in time a million. Now, it's not exact, and there's been a lot of doubt about exactly how this operates, but he gives a theoretical mechanism for these things, but there's no real observational data until people start drilling into ice cores and picking up changes in foraminifera and the pollen that's dropped, etc., into measurable beds. Now, Milankovitch calculated the solar radiation at different latitudes from the interacting changes in eccentricity, obliquity, and precession of the Earth as it goes round in the sequence. And Kroll also made the major error, it turns out, that he thought that what would cause an ice age is the minimum winter temperature. And that would occur when the Earth is furthest from the sun, the northern hemisphere is tilted away at that point, and the winter occurs when the Earth is at its furthest point, because that's how eccentricity, obliquity, and precession operate. So this is what the data look like from something astronomers can be. They're pretty sure this is exactly what it looks like. It's a 100,000-year periodicity in the non-circularity of the Earth's orbit around the sun, because of the different gravitational influences of other planets pulling the Earth away to make it slightly non-circular. It's about 1% off, 1.5% off. It's not dramatic. But as you can see, it has varied a lot over time. The obliquity has also varied a lot over time. Indeed, it appears from the data that I've got that it's got changing variance. So you can see that both of these time series are non-stationary, right? They're not, if you treated them as a stationary series, you would not get the right model out. The precession, which is due to the Earth not being an exact sphere, operates that if the winter season is when the Earth is furthest from the sun in the northern hemisphere, which is why we get, the southern hemisphere at the moment is like that, so it gets colder winters and warmer summers. We get milder winters and milder summers because we happen to be closer to the sun in the tilt at the time of the season that's currently operating. And then these have been translated into summertime insolation at 65 degrees south, which you can see reflects the basic features. They've got the two patterns of the eccentricity, and they've got the obliquity, and it's slightly hard to see the impact of the precession. I'm not going to use D, but I'm just going to show you people have tried to calculate what we might call sufficient statistics of the orbital behavior like that. Now, there have been very comprehensive systems by Robert Kaufman, who's here with Katerina Euselius, and Robert with Felix Pretis, who's my co-director of Climate Econometrics, and thanks to you for providing us with the data. Now, econometricians are dreadful with data. We tend just to take data. The data that are being used here have involved thousands of people over thousands of person years to get the data, to sort it out, to blend it across different, you can get it from the Antarctic, you can get it from Vostok. It's very hard to get the data, but they've done it, and it's all I have an underlying paper. I'm not going to describe it today, but it's all really important work. But many climatologists doubt that the orbital variations can be strong enough to start rapidly and close rapidly glacial episodes. But one of the answers to that is an open ocean surface typically absorbs about 6 times more solar radiation. You hear about the Arctic melting. The loss of high albedo from an ice-covered sea is really dramatic in how rapidly the temperature will rise in the Arctic, because the sea is now absorbing all that solar energy rather than it being reflected. The other possible reason for a rapid change is non-linearity. Now, it's not treated the way we treat it, excuse me, but I'm going to include non-linear interactions between the drivers. Not just the non-linear ones, but squares of them as well, but not the cubes, which I think now is possibly a mistake. Because if the Earth is tilting towards the sun at the time it's closest to the sun, it's going to be much warmer in the northern hemisphere than if it's tilting away. I couldn't find papers that explicitly did this, but they all talk about it. So these are the non-linear interactions. This is eccentricity and obliquity. This is eccentricity in precession, that's obliquity in precession. And the others are just to show that you get the same kind of effects coming out if you use a sufficient statistic. So what about the data that we're going to analyze? Well, top left is the pattern of ice volume over land. The next one is CO2 volume as deduced to be in the atmosphere from measures made on various ice cores. Then there's the temperature, which is deduced from the composition of the air. And then there's sea level that I'm not going to analyze, but it's pretty obvious that if a vast amount of the sea ends up as ice and land, the sea is going to be lower. It doesn't take much deduction. Now, one of the things that's confused this literature are the hugely high correlations between CO2 and ice. And since ice and CO2 are inversely related, I've taken the negative of ice, and that's in the top left diagram, and you can see they're incredibly highly correlated, which would be very odd if CO2 is not the cause of an ice age. Anyway, we'll come back to that. Then we've got CO2 and temperature in the top right, temperature and the negative of ice, and then sea level and the negative of ice. They're all very highly correlated. So if ice ages are purely due to orbital variations, why should CO2 levels correlate so highly with ice over land? And the answer is that the oceans hold about 60 times more CO2 than the atmosphere, especially the Southern Ocean, which acts as a carbon sink. And during cold periods, that gets locked in. But as the planet warms, it's like leaving a glass of sparkling water open. The CO2 comes out of it, and it comes out as the planet warms. So it's a derivative variable. It enhances cooling and warming, as you'll see, not very much from my estimations, but it's certainly not the cause. The cause is the orbitals. So we treat the orbitals as exogenous. They're going to drive temperature and changes in ice, and that in turn changes CO2. And to resolve this, we need to model it as a simultaneous equation system, with ice, CO2, and temperatures jointly endogenous, treating all the orbital variables in our nonlinear functions as inputs, lags to pick up the inertial dynamics, because if you've got 10,000 miles of ice 2 miles deep, it's not going to vanish in a short period of time, so the dynamics are going to matter. We're going to saturate to get rid of the outliers, of which is quite a large number. We're then going to select over the variables to get a parsimonious var, and then we're going to estimate it by full information maximum likelihood, which is sufficiently over-identified that I can include any pair of the endogenous variables in each of the equations simultaneously and get them all identified. And it turns out that's a pretty obvious thing for an econometrician to do, but I couldn't find anything in the literature. So it's a standard var x apart from the indicator saturation. The lags pick up the dynamic inertia. Remember, it's a 100,000-year orbit, and so 1,000 years is just 1%. The Earth is going to be very close to where it was 1,000 years later. So if there's a lot of ice, it's not going to change dramatically from that movement. We pick up, I use 0.1% because we've got 800 observations. I keep 100 that they're never used for estimation. They're always only used for forecasting, forecast evaluation. We pick up 35 indicators, but many of them or just to maintain encompassing of the first feasible gum. So we get quite high correlations between the variable and the fitted values, 0.98 for them pretty much. The correlations between the var-X residuals are very low for ice, CO2, and temp, but they're quite high between CO2 and temperature, and we'll see that that's going to matter. Then we select over the variables at 1%, because we don't have terribly many of them. We also select over the indicators in each equation, so the ones in each equation are only the ones that matter in those equations. Then we model it as a simultaneous equation, and what do we find? Well, despite including current CO2 and current temp in the ice equation, they're completely insignificant and are eliminated. But ice does depend on ice lag, there's a big coefficient, 0.86, and on temp lag, it's a very significant coefficient, T of 10. Depends on eccentricity and eccentricity lag, obliquity lagged, eccentricity times obliquity, and that lagged, and eccentricity times precession. And that's exactly what you would have deduced theoretically by reading the literature, right? It's all these interactions between where the Earth is relative to the sun and how it's tilting, and when it tilts, which season of the year. For CO2, we get CO2 dependent on CO2 lag, temp lag. Current ice and current temp do not come in significantly. Eccentricity and eccentricity lagged, obliquity lagged, just like ice. But then we get eccentricity times obliquity lagged, and obliquity squared comes in. That seems to really matter for how rapidly CO2 appears. And then for temperature, we get temperature lagged, and at last, a significant current dated coefficient on CO2. Then eccentricity times obliquity, and that lagged, and eccentricity times precession. Now, the crucial thing for me about this coefficient is, how do we interpret it? Well, A, it's positive. Imagine the CO2 is measured in parts per million, currently about 400 parts. During the Ice Age, it's about 300 parts maximum. So if we were to multiply CO2 by 100 parts per million, we get 0.8 of a degree. And that's roughly what we've had from 1958 to now for roughly 100 parts per million. So this coefficient is saying, over and above what's happening to the planet from natural forces, CO2 is increasing temperatures by about 1 degree for 100 parts per million. That's how I interpret it. But it's not that that's causing the ice ages, right? It's changing temperature. And of course, here it's endogenous, now it's exogenous. And we'll see that that matters. So, likelihood ratio test shows it easily satisfies the over-identifying restrictions, although there are 64 of them, and you can't reject the nonlinear function, you can't drop the nonlinear functions, and you can't drop the impulses. They're very, very highly significant. And this is what the data for the variables look like. The left column is ice, CO2, and temperature. The right column is the residuals, and then the forecast errors, which I'll talk about immediately. These are the model evaluation graphics. It's quite close to normal, a little bit discrepancy for CO2, but you'd expect that after IIS. Residual parallelogram's completely flat for ice. There's a little bump. It looks like CO2 depends on CO2 lagged 2,000 years, which is interesting because it's supposed to be taken out of the atmosphere much more rapidly than that, but the data says not. And then temperature is pretty flat as well. So these are the forecasts over the last 100,000 years in 1,000-year intervals, so there's 100 of them, together with the actual forecast errors, not scaled by the residuals, but actually what the errors look like. And all the forecasts lie well within the one step ahead confidence bands you'd have calculated from treating it as a simultaneous system. Indeed, it's very interesting. The root mean squared forecast errors for ice are smaller than those for the fitted equation for ice, even although we're going 100 observations out afterwards. They're slightly bigger for CO2, but they're smaller than if you'd done CO2 without indicators, but they're definitely bigger for temperature. So these are the 100,000 year ahead dynamic forecasts, right? Wouldn't we love to be able to do this in economics? I really enjoyed doing this study. So they're great up to about 20,000 years ago. You can see they're tracking really well. They mostly stay within the confidence bands until the very end, where CO2 and ice pop out. But they're for 2.2 standard errors because 10% of the explanation in sample was from outliers, and we can't do outliers in here because it's all ex ante. Now, the last two ice ages look very similar apart from their length. The top graph is the last but one, and the bottom graph's the last. You can see they've got very similar patterns. Now, Ruderman has suggested very strongly that humanity began to influence the climate 10,000 years ago, maybe even 12,000 years ago, when they started to clear the forests across Southeast Asia to grow rice, and they domesticated animals and started farming. So I'm going to zoom in on the last 10,000 years. I'm going to re-estimate the model up to that, and it actually passes all the tests. But the coefficient on CO2 has actually increased slightly to unity, which is still consistent with 1 degree per 100,000, per 100 parts per million CO2. Then we do the multi-step forecast, and this is what they look like. Now, they're all well within the confidence bands of the dynamic forecast, so the model's not non-constant, but it's obvious that something's happened. Here, they're all above, and they're mainly above. Here, they're all below, and they're mainly below. Here, they're mainly below, and mainly below. It's very systematic. It's not big, but it's very systematic. It is suggesting that Ruderman's right. Humanity has been affecting the climate over the last 10,000 years. Not much. It's actually here, it's for 20,000 years. Not much initially, but towards the end, quite a bit. Now, I also changed the status of CO2. Is CO2 really one of the causes? So I made it exogenous and did a two-equation model. And now the coefficient for CO2 is quite ridiculous. It suggests it's 0.24. So 100 parts per million would have blown the climate apart by 2.4 degrees. And it's implausibly large. And I think the evidence here says it's jointly endogenous. It's a response to the orbital drivers jointly with ice and temperature. Now we come to really staggeringly non-stationary data. This is the data on the United Kingdom's CO2 emissions, and I'll show the fossil fuel usage in a moment or two. And it starts in 1860. We went below the level of 1860 in 2013, and now we're well below it. It rises dramatically, it oscillates violently in the interwar period, rises again, and then it plunges from about 1975 onwards. That's partly mirrored by the usage of coal, but it's also affected by the usage of oil, the usage of natural gas, and more recently by solar. The ratio of Britain's CO2 emissions to the capital stock's been remarkably dropping. It's dropped by 82% since 1860, and that's efficiency gains we've had in the level of output we can produce from the capital stock without producing too much CO2. Now, over this period, much of this CO2 is being exported. People talk a lot about, oh, you know, you've got to deal with imports of CO2. This is all Britain sending trains and steel and rail and cotton to other countries. It's exporting a huge amount of it. So it's a lot of that actually isn't internal, and a lot of this towards the end isn't domestic, but it's very hard to adjust it. So the data is varying all over the place, really quite dramatically. And these are the distributional shifts that we see. Well, let me go back. Look how large that looks. Then you put in the next period, and it now looks tiny, and it's shifted off to the right. The next period, it shifts off, but it's actually split. There's quite a lot going back to the left. And then the final period is way back to the left. So the distributions are shifting. There are, if you like, location shifts that are quite large throughout. So I'm going to model this by including CO2 emitters, oil and coal, linearly for linear CO2, then the capital stock and GDP, but they're going to come in log linearly. Dynamics for adjustments to technology, they're really, really important, as you've seen from the capital stock. Legislation is very important, and I don't have any decent data on fuel prices, so they're going to be picked up, both by dynamics and impulse and step indicators. The indicators are only going to capture features not explained by the variables, but we do have to allow for the possibility that some of the huge variation you saw are due to indicators. Now, I have a previous model of this that's listed in VoxEU, and it used linear GDP and linear capital, and I've put them in the red lines here, and then I've put in blue the log linear ones. And you can see what the problem is with the linear, that here, this is one of the biggest drops ever in British GDP, but it looks tiny in linear. And this is a huge change in nominal, but hardly any change in the log, because of course, a billion change in GDP today is not very big, but it'd be about 10 times GDP in 1860. And the same with the capital stock. And it's really improved the model dramatically to deal with the logs. So we select in 4 stages. First of all, the step indicators at type level. We check the model's working. We then select over the economics and fuel variables. Then we derive the co-integrating relationship, because this is co-integrated. Then we estimate and evaluate the non-co-integrated formulation. I'm going to skip this. It picks up 5 impulses in 4 steps, and everything's coming out perfectly sensibly. There's no additional non-linearity, which there had been in the previous model. And we can divide at least 2 of the steps into 1. The steps for an indicator for 1926 and a step for 1927 become a change in an impulse in 1926. And the 2 impulses for 47 and 46 become a change in the impulse. And then we get the crucial 3 large step indicators that are identified with very major events in the UK. The 1926 Act of Parliament that created the UK's nationwide electricity grid, before that it was a free-for-all and enormously inefficient. And this act has lowered the average usage of electricity ever since by having it common across the country. 1969, we gave up using coal gas and started using natural gas because it had been discovered in the North Sea. And that required the conversion of a lot of equipment. And frankly, we ought to convert it all back, because coal gas is mainly hydrogen. We should convert back and use hydrogen rather than natural gas, which is methane, which when you burn it gives off CO2. So it's been a big impulse to CO2. And then 2010 follows the UK's Climate Change Act of 2008 and the EU's Renewable Directive of 2009. And it takes a time for people to react to these, but they've had a very dramatic effect on what's going on. Now, the Climate Change Act was cross-party and almost unanimous in Parliament. Almost everybody in the British Parliament, however stupid you might think it now is, was actually very sensible about climate change back in 2008. Now, we don't impose that these indicators pick up the policy effects. The data tell us it does. And we think 2010 is almost certainly the response to the Climate Change Act. So then we select over the variables, we keep them all, they're all significant. Then we do a unit root test on the equation. We can estimate the long run. The long run's interesting, it's a much better long run than previously. Roughly, emissions are twice times coal. That's roughly the CO2 content in pounds of CO2 per pound of coal. That's roughly the one for oil. These are then the roles of capital in GDP. GDP did come in significantly negative in levels. It's still negative, but it's completely insignificant. And then we get the big effect, much higher up to 1969, much higher up to 1925, much lower up to 69, and then there's an intercept. And that forms a very strong co-integrating relationship. Indeed, the co-integrating relationship almost describes the data on its own, right? If you look at the graph of the implied co-integrating relationship, plotted against the data, it's picking up almost everything, and it's certainly a stationary time series. And then we come to the model I will dwell on a little bit longer. We have when you burn coal, you give off CO2. It's slightly smaller than you might expect, 1.88 rather than 2. That might be measurement, it might be exports. Same for oil, that's roughly correct for oil, it's about 1.6. Change in capital is hugely significant. We get 7 units for all the percentage change. Remember, I've actually multiplied K and G by 100, so delta K and delta G here are percentage changes. 7 and 0.86, so capital is vastly more important. Then there's the feedback, which is hugely significant. Now, I didn't include 2010, the climate change variable, in the long run because it only got 2 observations. If we'd done the steps the other way, I'd have had 2010 and 2011, and that's it, because that's the end of my estimation period. So it's picking up an intercept shift, if you like. And then there's the indicator variables. And this is what the track looks like in changes, which is very hard to interpret, but it's pretty normal residuals and pretty flat parallelogram. But if I put it into levels, you can see it's picked up very well. That's the 25, 69, and 2010 effects. But despite the fact that GDP is irrelevant, you can derive a Kuznets curve, as it's called. It's meaningless in my view. It's implied by the model, and it tracks it vastly better than any fit of any Kuznets model I've seen. So the axis, the left axis, is CO2 emissions in millions of tons, megatons, and then the other axis for the Kuznets mimic is GDP, and as you can see, it comes down as GDP is going up. But that's nothing to do with GDP because it's insignificant in the model. It's because of technology. If we developed solar cells back in 1400, we might never have had a climate change problem if the technology had been available. However poor people were, they could still have discovered electricity, discovered how it worked in fuel cells and solar cells, and done it back then. They didn't happen to do it. So that's why it's coming down. And then we can do a nonlinear versus linear encompassing test. It appears to slightly reject. M1 is my current model, M2 is a model Neil Erickson is now using to get the Fed to take climate more seriously. It looks as though it slightly rejects, but in fact, it's only rejecting at the 5% level, whereas I was selecting at 1% level. So if you put in the variables from his model into mine, they're actually not variables that would be selected by the procedure I'm using. Then we can get the one-step and dynamic forecasts out of the model. And as you can see, the fans are for the one-step forecast after step indicator saturation, treating the policy shifts. And the error bars, if you don't do that, there's a huge reduction in the mean square error. And the lower graph is doing this dynamically. So these are dynamic forecasts, but they're coming out of a vector autoregression in order to do it dynamically. So coal, oil, capital, GDP, and CO2 are all being jointly done. And it works extremely well. And surprisingly, the root mean squared forecast error is almost unaffected relative to the single equation. So it does suggest it's quite a good specification. How long have I got, Claudio? 10 minutes, okay. How well is the UK doing? Now, the Climate Change Act aimed at 80% reduction in CO2 emissions by 2050. It was the first legislation in the world saying, get out of CO2 or we'll fine you enormous amounts of money. First with coal, later it'll be oil and gas. Now they've reduced that to zero, right? It's going to be zero by 2050. I'll comment on that shortly. I'm pretty skeptical. So I've plotted in the left-hand graph our CO2 emissions against the target that was set by the Climate Change Act. And as you can see, the red line is way below the blue line. We're way below our target in 2018, which is the latest data we've got. So even given the target for 2020 is going to be much lower, we're going to be way below the target for 2020. So we're doing far better than even the Act wanted us to do. But that's it, folks. That's the easy lifting. It's getting rid of coal. We've gone from about 250 million tons of coal a year in 1975. Last year, it was 4 million tons. Getting rid of coal's got rid of a lot of the CO2 production. Then I've simulated what do you need to do to get to an 80% reduction. And the answer is you need no coal, you need 75% less oil and 75% less gas. You need a 50% reduction from agriculture, construction, and waste. And then I've compressed these into 5-year intervals so they're not spread out for miles. And given the bands around them, and it's just about possible by 2050 to get to 80%. How you get 100%, I frankly have got no idea, particularly if you want to add back in the embedded CO2 in the UK's imports minus the embedded CO2 in its exports. It's going to mean zero on everything. And I don't know how you get zero in construction, waste, and agriculture, never mind transport and manufacturing. So what do I conclude? Well, I conclude that the kind of tools we've got work. More candidate variables and observations is not a problem. The econometric approach has seen many successful applications, but it's crucial to take account of the non-stationary nature of time series, both stochastic trends and distributional shifts. And the fact that macro sticks to believing in equilibrium is actually unbelievable when it couldn't forecast what happened after 2008 and will not forecast what happens in the next recession because they refuse to deal with the fact that the world is extremely non-stationary. And I think that's one reason central banks have been so slow to embed climate risks into macro models. And I do wish there was anyone got any connection with central banks to go back and say, look, this is ludicrous. Climate risks are gigantic. They're going to affect the financial system, the output system, the manufacturing system, the investment structure, affect financial markets. You've got to take account of it, and that's going to obviously be non-stationary. Now, the econometric tools have been effective. We can model energy balance systems of the climate as a CVAR. That's one of the papers in the special issue that Eric referred to by Felix Brettes. We've detected the impacts of volcanic eruptions and temperature and really got the volcanologists and dendrochronologists quite excited about using these tools. We've shown that accurate hurricane forecasts really do help mitigate the damages that a hurricane costs. And we've shown that estimated costs of temperature changes from 1.5 to 2 degrees are quite serious. Now, the software has recently been made available in a program we call Excel Modeler, which is an Excel add-in. It's almost been given away. You can download it from Jürgen's website or the Excel Modeler website that I've quoted here and try it out for free to see if you like it. And then it gives you all the availability that I've talked about of these tools in order to model things in a framework that perhaps your business school students or your undergraduates could actually do because they probably know how to use spreadsheets but aren't willing to learn quite complicated software. Thank you.